All right, let's go ahead and do chapter 20. Chapter 20 is carboxylic acids and nitriles. There's really not much on nitriles. The lab that we do on Wednesday, believe it or not, is actually contemporary because it will concern nitriles and convert a nitrile to a carboxylic acid. This is one in a row. So that's on page like 360 or something like that in your book. And it's benzonitrile. Oh, you get, oops. I have my original. If you need one?
I need one.
Yeah, I have my original. Now, the one that's online, the handout that's online, also has about 7 or 8 pages at the end that has problems and a review and stuff like that. So if you didn't print that, you might want to at least print those pages so you have something to practice with. Any questions before we get started? Carboxylic acids. We've seen carboxylic acids. We've used them all semester. Acetic acid, benzoic acid. This is linoleic acid. Everyone, I'm sure, has heard of cis and trans fatty acids. You'll note that the double bonds here have cis stereochemistry. The dreaded trans fatty acids are obviously trans at one or more positions. And the trans fatty acids are very difficult to metabolize. Cis, very easily split by lots of enzymes. Trans are not. So trans just kind of get in you and they stick. So they're bad things. Nomenclature, very simple. You're going to take the name of the alkane. You're going to drop the E on the end, and you're going to replace it by 2 words, oic acid. You drop the E, put oic, and the 7th word is acid. We'll get a number at the end closest to the carboxylic acid. As always, we're going to list substituents alphabetically. If we have a ring, benzene ring, cycloalkane ring, whatever, and we have a carboxylic acid attached, we will simply add the word carboxylic acid to the ring. This we all know is acetic acid, the acidic component of vinegar. We have 2 carbons, so it's a derivative of ethane, isn't it? We're going to drop the E, put an oic acid on, and we will call this ethanoic acid. Eth, 2 carbons, and fully saturated oic acid, it's a carboxylic acid. This, of course, is benzoic acid. We've used it many times. We'll use it again on Wednesday. This is a ring. Therefore, this is going to be a benzene parent, and we're going to add carboxylic acid to it. Benzene carboxylic acid, 3 words. Benzoic acid is also IUPAC approved. So we can use benzoic acid as a parent, just like we can toluene, and name substituents around the ring. Any questions? Well, let's go ahead and do a set. Very quickly jot down appropriate names for these guys. Remember, your parent chain needs to contain the carboxylic acid. Carboxylic acid is going to be attached to carbon number 1. And this one down here in the corner, we're going to name as a derivative of benzoic acid. Hello. All right, our first one, we look and we find our longest carbon chain containing the carboxylic acid. That's going to be this guy here. And the carboxylic acid is going to be carbon number 1. We have 1, 2, 3, 4, 5. So the parent is a pentane, so it's a pentanoic acid with an ethyl group dangling off in carbon 2. 2-ethyl pentanoic acid. Yeah.
So you don't have a dash between the ethyl and the pentanoic acid, it should just be one?
But pentanoic and acid are 2 words.
Right, just the ethyl, oh.
Now, the ethyl pentanoic. If you had 2-ethyl pentane, it would all be 1 word, right?
I'm getting confused.
You see, you can never forget organic 1. Our next guy here, same sort of thing. This is going to be carbon number 1. And we're going to have 1, 2, 3, 4. We choose this instead, or this one instead of this one, because this will give us 2 substituents. Remember, UPAC likes substituents. So this is a 1, 2, 3, 4. That's a butanoic acid. It's a butanoic acid with an ethyl group in carbon 2 and a bromine in carbon 3.
Was it really good, Dr. Young, get the more substituents? Why didn't you go the other way, you said?
Well, if we went this way, we would only have this 1 bromoethyl substituent, only 1 substituent. UPAC wants the greatest number of substituents. Same rule that we use for alkanes. This is a cyclohexene, isn't it? Now, previous to this, we would have started numbering at the double bond and numbered through it, correct? But remember, the carboxylic acid is going to get carbon number 1 status, which means our double bond is now in carbon number 2. This is going to be a cyclohexene carboxylic acid with the double bond in the position number 2. And finally, we said we're going to name this last one as a derivative of benzoic acid. This obviously has to be carbon 1 if it's a benzoic acid, putting a methyl in carbon 2, and the bromine here in carbon number 5. 5-bromo 2-methyl benzoic acid. Now, as always, we're not going to do much in the way of nomenclature for exams. It's going to be fairly simple and straightforward, but just make sure that you understand the basics of our rules. Any questions? Well, carboxylic acids. We have a carbon-oxygen double bond. We have a OH attached to the carbonyl carbon. The oxygen and the carbon here are going to be sp squared, which means that our bond angle is 120 degrees. It's also planar. Remember, we have electrons in unshared pairs of electrons here in the plane of the board, and we have a pi system coming out here towards us and away. Standard carbonyl. Carboxylic acids are really, really good at hydrogen bonding, almost as good as water. The reason is, and you can actually see it on this example here, carboxylic acids can both be a hydrogen bond donor and acceptor. So the geometry is such that they can pair up very nicely. We can form very extensive hydrogen bonded networks. Because of that, carboxylic acids are high boiling for their molecular weight. It also means that the infrared spectrum of carboxylic acids is going to be dominated by a very broad OH stretch. We'll see that in a little bit. Again, that arises because of the hydrogen bonding. When you ionize a carboxylic acid, you make a carboxylate anion. Carboxylate anion, we have two equal bonds here in the anion. This is a resonance hybrid, so the charge is spread out equally over both oxygens. This is the resonance diagram here. Again, we just move electrons in and up, and we move the charge from one oxygen to the other. Again, both in the resonance hybrid, both bonds are equal, and we have half a negative charge on both. I will say this several times. The thing that makes really anything acidic, and we're speaking specifically of carboxylic acids now, is the stability of the anion. The more stable the anion, the more acidic the species will be. Here we are stabilizing this by resonance, and that's why these are acids. Now we all remember from general chemistry that we can write an equilibrium ionization. It's going to simply be products over reactants, and again, we do not include water because it's a liquid. So the acid dissociation constant is simply the concentration of acetate anion, hydronium, over undissociated acetic acid. Now, acetic acid, all carboxylic acids, are what we refer to as weak acids. There are a couple that are pretty much on the borderline of strong acids, but acetic acid is a weak acid. Now, remember what a weak acid means. It refers to this equilibrium. In a weak acid, we have very little of the anion and hydronium, and most is here undissociated. Therefore, this equilibrium constant is typically very small. The products over reactants is about 10 to the minus 5. That means that, maybe a 1,000,000 to 1 ratio or something like that for this to this. Almost all of it is present as the acetic acid, a little bit of hydronium and acetate. Now again, back to general chemistry. When we speak of acid dissociation constants, to make it handy, we use pKa. Remember, the little letter P simply refers to negative logarithm. So the negative logarithm of Ka for acetic acid is about 4.76. Now in reality, the pKa changes. It's an equilibrium constant. It changes depending upon conditions. So you'll see this quoted everywhere from 4.61 all the way up to 7,6. But again, it's a very shifted equilibrium, mostly undissociated acid. With pKa's, remember, the smaller the value, the stronger the acid. Now let's look at 3 substituted or 3 carboxylic acids just to strengthen this. This is acetic acid. And like we said, the pKa is about 4.76. If we take and we add a fluorine here instead of a hydrogen, we get fluoroacetic acid. Fluoroacetic acid. Fluorine is very electronegative, isn't it? That means that it's going to remove electrons from our anion. If it removes the electrons, it makes this more stable. Hence, this is a stronger acid. pKa drops from 4.76 to about 2.3. If we go all the way and put 3 carboxylic, or 3 fluorines on, we get trifluoroacetic acid, and this is down pretty much in the range of a fairly strong acid. pKa of about 0.2. Remember, if the pKa was 1, we would have equal concentrations on all sides. So, again, the more electron withdrawing substituents, the more stable the anion, the stronger the acid. Yeah.
I was a little confused because I read the book last night, which I'm kind of upset about now, because it was confusing where I didn't quite understand how they were trying to say that, like, if it's more stabilized, it dissociates more or less.
If the anion is stable, the more stable the anion, this equilibrium is going to be shifted towards the anion. When you shift the equilibrium towards the anion, you also make hydronium. More hydronium, stronger the acid. So you stabilize the anion, you get more of this stuff, stronger acid.
Oh, because they were talking about, like, in, just like within water, and so it's like it dissociates more if it's a stronger acid.
Yep. In a strong acid like HCl, this equilibrium is virtually 100% this way. And there's virtually no undissociated Bronsted acid. In a weak acid, it's reversed. Here's a nice set just to look at. We know that an alkyl group is electron donating, isn't it? Remember this from electrophilic aromatic substitution. Therefore, this is a weaker acid than acetic acid. And as we put things on that can withdraw electrons, we get a stronger and stronger acid, finally down to trifluoroacetic acid, which is the strongest of the acetic acid family. Any questions? Now, speaking of electrophilic aromatic substitution, we can also use this as a mechanism to review substituent effects. So why don't you look at this collection here and decide which is going to be the strongest acid, which will be the weakest acid, and see if you can pretty much put the others in an order. Remember, electron withdrawing substituents will stabilize the anion. If you stabilize the anion, you make it a stronger acid.
So just look at the periodic table and work your way.
Not the periodic table, remember your substituent effects in electrophilic aromatic substitution.
It's not chapter 15.
Chapter 15, right. We know that things like halogens, a nitrile group, are going to be electron withdrawing, aren't So if this was an anion, it would stabilize it. Same thing with nitro. Same thing with an acetyl group here. Oxygen, we remember, pumps electrons into the ring by resonance. Therefore, it's going to make the anion less stable. Just on our limits here, the most stable anion is going to be the guy with the nitro on it. Because remember, a nitro group withdraws electrons by resonance from the ring and also from the anion. Remember, things like oxygen can donate electrons by resonance, pushing electrons into the ring, making this less stable. If it's less stable, it is a weaker acid. More stable the anion, stronger the acid. So our strongest acid is going to be here with nitro, isn't it? Then we're going to go through things like the cyano, the acetyl, the carbonyl here, the chlorine. Going to hit the benzoic acid in the middle somewhere, and this is going to be our weakest acid. The collection should look like this. Most stable anion, strongest acid, least stable, weakest acid, and there's our set. Again, it's just a nice review of electrophilic aromatic substitution. These guys deactivate the ring. This activates the ring. Any questions? You can probably expect a question or two about relative acidity. On the exam, once again, the rule of thumb to always remember, the more stable the anion, the stronger the acid.
If there was a fluorine attached to that ring, where would it be?
Fluorine, it would be right here around chlorine. Probably right in here somewhere. All right, I said carboxylic acids hydrogen bond nicely. Because of that, they form dimers. They'll actually even form dimers in the gas phase, believe it or not. They really do like this complementary hydrogen bonding. Because of that, if you have a compound with a carboxylic acid, it is notable for being incredibly ugly. In the OH region here, we have this very, very pronounced OH stretching. This goes all the way from like 2,700 up to 3,500 as this big, broad thingy. And this is actually a fairly kind spectrum. Carbonyl is the same thing. Carbonyl, because we have hydrogen bonding, doesn't show here, but it's a very, very broad, ugly peak looking like this. Last week we made a carboxylic acid. I thought about doing an IR, because that would be fun, but the IR of the carboxylic acid is just, like I said, so incredibly ugly that you don't even want to see it. Big, broad peaks everywhere. NMR is much different. In the NMR, the carboxylic acid proton is the most highly shielded in the proton NMR. Aldehydes come about 10 parts per million. The carboxylic acid proton is a singlet at about 12. Very characteristic. Nothing else comes down this far. Something like a methyl group attached to a carbonyl carbon here, nothing unusual in the 2 to 3 range. For the C13 NMR, We know that aldehydes and ketones are typically about 200 parts per million. The whole acyl family. Now, in this next couple chapters, we're going to do the introduction to the term acyl. They're all carboxylic acid derivatives, but they tend to be in the 170s. So if we look at acetic acid, our methyl group here is about 20 parts per million, and this is 176. So very easily distinguished between aldehydes and ketones, the whole acyl family, right in the 170s. Any questions? All right, here comes a really fun little problem. A little spectroscopy problem. Here we have something, C8H8O2. Only thing I'm going to give you is a C13 NMR. From that, you can easily deduce the structure. Think about it for a minute. First thing you want to do, of course, is to look at the formula. How many degrees of unsaturation do we have? We ignore the oxygen. We would have 5 DU. So that should tell you right away that we're probably dealing with a benzene ring, and that one of these oxygens is going to be a carbonyl. Now, if we look at the C13 NMR, I have these grouped for you so very nicely. Looking at our quartet here, we have a quartet. It's moderately shielded, so about 22 parts per million. This is going to be a simple methyl group. The next group tend to come between 127 and 142. We remember that this is the region where we have carbons that are part of a benzene ring. Now again, from our DUs, we more or less expected that. And then finally, looking down here, we have the singlet at 172. That's a carbon with no hydrogens attached. Again, we're at 172-ish. This is going to be a carboxylic acid carbon. Now you might ask yourself why I say carboxylic acid. We have 2 oxygens. It could be an ester too, couldn't it? Well, I suppose it could be, but we know that it isn't. How do we know it isn't?
Because ketones and aldehydes are 200.
No? No? Think about the aromatics region.
Because oxygen will be in the
We have 2 singlets in our benzene region, don't we?
That's
Because we have 2 singlets, that means we have 2 things attached to our ring. So, carboxylic acid must be one of them, and the methyl group must be the other. Now, we can actually use a C13 here to figure out the substitution pattern. Think about your 3 possible isomers. We could have 1,3, 1,4, or 1, 2? The question you ask yourself is how many different ring carbons are there in each of these? Figure that out. How many ring carbons in each of these isomers? No, not 12. There are only 6 carbons. It's our symmetry exercise, okay? We've done this, we do this all the time with C13. Here, this carbon is attached to the carboxylic acid. This carbon is in between these two guys. This one is attached to a methyl. This one is next to the methyl across from the carboxylic acid. This one is next to the carboxylic acid, and this guy is left over. There are 6 different carbons in this ring. Do this one. Attached to the carboxylic acid, attached to the methyl, next to the methyl, next to the carboxylic acid. Now there's no plane of symmetry here, is there? So this one, which is 2 away, is different from this one, which is 2 away this way. Again, 6 different carbons. And finally, our 1,4. Now we have a plane of symmetry, don't we? Right down the middle here. So we have this one attached to the carboxylic acid, this guy to the methyl. Both of these are adjacent to the methyl. Both of these are adjacent to the carboxylic acid. There are only 4 carbons in this ring. Now think again how many carbons there were in the aromatic region. There were just 4, weren't there? So from this very simple little logic exercise, structure must be the 1,4 isomer. 4-methyl benzoic acid, also called para-toluic acid. Any questions?
Yeah. But we also have figured it out from what we learned past. I forgot. It was the one where it was like 1 4.
Yeah, and this is the same exercise. 1,4 will give 4 peaks, 2 singlets, 2 doublets. 1,3 will give 6 peaks. 1,2 will give 6 peaks.
Wouldn't you be able to just automatically assume would be that?
I'm sorry?
Wouldn't you automatically be able to assume would be that way because it's a strong activity and it would be there?
No, the activation thing is your plane of symmetry here. Again, these 2 carbons are identical. These 2 carbons are identical, and these 2 are unique. These are both doublets. These are both singlets. All right. We're going to do reactions that yield carboxylic acid. And like I've been saying all semester, you already know most of these. Okay? That's reassuring to you, right? Because you already know these either from things we've done this semester or from Organic 1. Think about oxidation of aromatic side chains. We did this back in chapter 15, maybe 14. We know that as long as we have a benzylic hydrogen, that is a hydrogen in the carbon adjacent to the ring, that if we dump in permanganate, neutral permanganate, warm it up a bit, we will oxidize the alkyl group. No matter what's attached, you wind up with benzoic acid. If your benzoic carbon has at least one hydrogen, it goes to benzoic acid. If it doesn't, nothing happens. In chapter 17, we talked about oxidation of alcohols. If we have a primary alcohol in the presence of Jones reagent, which is basically just chromate and acid, we oxidize the primary carbon to the carboxylic acid. Chapter 17. Primary alcohol, chromate, carboxylic acid. Any questions? We also know from chapter 18 that if we have an aldehyde and we try to use chromate, that the aldehyde will immediately and very rapidly oxidize to the carboxylic acid. Remember, if we wanted to make an aldehyde from an alcohol and stop there, that's when we use pyridinium chlorochromate, PCC. That's a very mild oxidizing agent. Your standard chromates go all the way to the carboxylic acid. Chapter 17. There's also a very sweet way to convert an aldehyde into a carboxylic acid. And this is the basis of what's known as the Tollen's test. Okay, now this is one of the really fun things that we used to be able to do in lab. Aldehydes can be oxidized by silver oxide in the presence of ammonia. You need ammonia there to form a chelated silver. This reagent oxidizes aldehydes specifically to the carboxylic acid. Now what's neat about it is that we're left with metallic silver when we're done. The thing that you do in lab is you take a nice clean piece of glassware, you take silver oxide in the presence of ammonia, and you add your aldehyde. You actually use this as a test to see if it is an aldehyde. If it is an aldehyde, as the silver is produced, it will form a very thin mirror on your glassware. Let's watch. Here we have the reagents. This is the aldehyde. Going to dump in ammonia. This is silver nitrate in here, actually. Now that gives you your silver oxide ammonia complex. And then you add the aldehyde. See it turning a little brown and ugly. Stopper it up. And then you want to shake it. You have to be patient.
Yeah, like 20 minutes patient.
Is the pressure you see in there?
you're done, by George, it's a mirror. Isn't that just the neatest thing? The Tollen's test. So if you have something you think is an aldehyde, you simply dump in silver oxide, ammonia, and see if you get your silver mirror. Now, I said that we used to do this in lab, and again, it was such great fun. The reason that we don't anymore is that everybody made one of these, and they were just so proud of it. I mean, it really is neat. It just really is neat. And so you take it and, you clean it out, and you stick it in your drawer so you can show your grandchildren someday. Unfortunately, the thin mirror coating can react with oxygen and form a peroxy compound, which means that it is explosive. And so it doesn't happen often, but somebody could have their little mirror in their drawer, and then after a few months or so, accidentally drop it, and it kind of like goes kaboom. So we can't do it anymore. I mean, that's a shame. And it was absolutely no fun to take it and then add silver or nitric acid and dissolve the mirror off, because that's no fun. But the mirror really was neat. All right, here's a reaction that we learned way, way, way back in Chapter 6 of Organic 1. All we did was we took an alkene and we reacted it with acidic permanganate. What we said happened in those days, still does happen, was that we simply split our double bond. Now we had a rule. If we had alkyl groups on both sides, we wound up with a ketone, right? If we had a hydrogen on one side, that was going to be oxidized first to the aldehyde, but the aldehyde immediately reacted with the permanganate to give a carboxylic acid. And finally, if we had two hydrogens, this was oxidized all the way to CO2. Chapter 6. Basically, we're just using permanganate to burn our double bond. If we have a hydrogen, we get a carboxylic acid. If we have two hydrogens, we get CO2. Again, if we have two alkyl groups, we get a ketone. Now, acidic permanganate is actually strong enough to even attack the ketone. And this is actually an industrial way to make carboxylic acids. If you take something like cyclohexanone, from our previous slide, we would say that, okay, this is the ketone product. But if you take it and you continue to heat it up in the presence of acidic permanganate, what happens is you actually split the carbon-carbon bond that's adjacent to the carbonyl. So let's just split it here. And when we do that, both of these carbons wind up as carboxylic acids. This is hexadioic acid. We will use that later this semester to make nylon. So industrially, this is an important thing. Any question?
Is this the like opening of a ring?
It's a complicated mechanism, okay? Permanganate is a very, very strong oxidizing agent, and if you heat it up in the presence of acid, you can chew up almost anything. This is the reaction we're going to do on Wednesday. If you take a nitrile and you expose it to aqueous acid. What happens is we oxidize the nitrile group to the carboxylic acid. The oxidation state of the carbon is the same in both. So nitriles and carboxylic acids are paired together quite often. This is actually a nice simple way to make, to do synthetic conversions where we need to add a carbon to our compound. We know that cyanide, Cn minus, is a good nucleophile, isn't it? Good nucleophile. So if we had like a halogen or something here, we could do an SN2 reaction, add the cyanide, then hydrolyze the cyanide to carboxylic acid, and we could do more chemistry. Again, we've added a carbon to our previous chain. So it's a nice, useful reaction. We'll actually do a problem like that at the end of the month. Any questions? Finally, one of the cutest ways to make a carboxylic acid from something like a bromoalkane is a Grignard synthesis. What you do is you take your, in this case, bromocyclohexane, add magnesium, and make a Grignard reagent out of it. Now, the Grignard reagent we recognize as a carbanion, right? This carbon is anionic. Turns out that CO2 is a very reactive compound at the carbon. Think about it. It's two carbonyls together, isn't it? We know that carbonyl carbons undergo attack at the carbon, right here, right? So, you make a Grignard reagent. Then you take little chips of dry ice, and you add it. The Grignard reagent, as a nucleophile, attacks, and we go up to our carboxylic acid. Really cute little reaction. Any questions? Now again, most of these you know. The two you didn't know were hydrolysis of a nitrile and carboxylation of a Grignard. But everything else is either from Organic 1 or stuff we've done now. Very quickly, these are oxidations. Draw products for these oxidation reactions. Our first reaction, oxidation with acidic chromate. Our Jones reagent. We know that a primary alcohol, this guy right here, is going to be oxidized to a carboxylic acid. That means that this carbon will be the carbonyl. We'll have a CH2 and then a ring, and it will look like that. Here we have permanganate and an alkene. Once again, we know we are going to split our double bond in half. If we have a hydrogen, this is going to be a carboxylic acid. two hydrogens, this is going to be CO2. And finally, we know that aldehydes are very susceptible to oxidation. Let it sit out in the air, it'll oxidize. In the presence of chromate, very easily oxidizes the carbonyl carbon here all the way to the carboxylic acid. Any questions? All right, reactions of carboxylic acid. Now, these are going to be new. These are things specific to this chapter. Probably the most useful reaction of carboxylic acids is simply the conversion of that into a carboxylate ester. This was done, or at least is named, after Emil Fischer, the very famous German organic chemist, who did a whole lot of work on elucidating the structures of carbohydrates. In a Fischer esterification, what you do is you take carboxylic acid and an alcohol. Remember, in ester, we replace the hydrogen here with an alkyl arrow group. Okay? So, we're going to take our carboxylic acid, usually in the presence of a fairly strong acid. The point of having the acid there is to make this carbonyl carbon even a better electrophile. So we do that by putting a proton here. That makes a lot of positive charge here. Now, in the presence of your alcohol, any old alcohol will do, this is going to attack, and we will get an intermediate, very unstable, but this can lose a proton to give this neutral intermediate. This is halfway to an ester. Now, in chapter 21, I believe, we're going to do acyl transfer. All acyl transfer reactions are going to go through mechanisms similar to this, and we form this guy, which is called our tetrahedral intermediate. We've gone from sp squared to sp cubed, tetrahedral geometry. This is the key intermediate in all acyl transfer. So in Fischer esterification, once we get here, remember we still have acid present, so we're going to protonate our OH group. That makes this a really, really good leaving group. Why? Because it can leave as neutral water, right? That's good. This will kick out water. We get, again, something analogous to this, loses its proton, and by gosh, we're at the ester. So what we've done is, we have taken carboxylic acid and an alcohol, we've made an ester and 1 mole of water. Now you'll note that I put equilibrium arrows everywhere here, right? That means if we have an ester and we want to make the acid, all we do is add a whole bunch of water. That pushes the reaction this way, and we hydrolyze the ester. If we want to go this way, we find some way to remove the water that we've made, There are tricks you can do this. You can do water separation using a distillation approach. You can put in an absorbent that will specifically grab the water, remove it from solution, and push it very nicely down this way. Water separator is probably the neatest. We're not going to do that. Very standard reaction. We've actually made a carboxylic ester a couple labs ago when we did the banana thing. Fischer esterification. Remember, it's equilibrium. Add water, go back. Take water out, go forward. A very elegant way to make a methyl ester, it only works for methyl esters, is to use something called diazomethane, CH2N2. This is a difficult reagent to work with. It's sensitive and stuff like that. But the yield here is essentially 100%. So if you have spent the last 4 years of your PhD thesis making a carboxylic acid, and to graduate you need the ester, this is what you do, because it really works. You just dump these things together, simple SN2 chemistry, and you get the ester. Now we can also make esters using good old-fashioned SN2 reactions. Remember, the rules of SN2 still apply. So this is chapter 3 or 4 from last semester, where we're doing simple SN2 chemistry. We need a very unhindered or activated alkyl group, so methyl works fine. Benzyl works better, allyl works fine, etc. Something you can do a good SN2 on. And basically the carboxylate anion simply attacks and you make the ester. Very simple SN2 chemistry. Go ahead, draw the product. Again, this is an allyl bromide. We know that the allyl group is very activated towards SN2. We will make a carboxylate ester. The O- will attack the allylic carbon. Bromine will leave, and we will make the ester. This is the allylic carbon. Here it is, simple SN2 reaction. Now the real way to make things like esters and almost everything else isn't to use a carboxylic acid, to be honest. Carboxylic acid is, the carbonyl is not activated enough towards nucleophilic substitution. That's why to do Fischer, you have to dump in all that acid. What you actually want to use is something like an acid halide. There are two acid halides that we would commonly use. One is an acid chloride, the other is an acid bromide. It's not on the slide here, but in order to make the acid bromide, we would use PBr3. Same thing we used back in alcohols to make alkyl halides. So thionyl chloride simply reacts with this to give the acid halide. Now think about this carbonyl. This guy had a partial positive charge to begin with. Now we put electronegative chlorine on it. So this is really, really hot. when it comes to being an electrophile. Acid chlorides are the things that you would use, and we'll do this in acyl transfer to make esters, amides, and whatever. Another way you can do it is what's called an exchange reaction. You can use oxalyl chloride, this guy, or phosgene. What happens is we attack, get a rearrangement, the halogen goes over, and you make the acid chloride. Phosgene, of course, has the problem that it's a World War I gas, and you don't really want to be using it unless you have to. And frankly, oxalyl chloride isn't much better than phosgene in terms of being a really nasty thing to use. Thionyl chloride or PBr3 work very well. When we made an ester, we did it using acetic anhydride, remember? We took an alcohol, reacted with acetic anhydride to make a carboxylic acid anhydride. All you do is take 2 moles of acid, split out water, and join them together. Again, if you have an anhydride and you want the acid, you add water, it goes back. If you're here and you want the anhydride, remove the water, it drives the reaction. Nicest way to make anhydrides is to use an acid chloride, which we made in the previous slide. React that with carboxylic acid, pyridine. You need in there to soak up hydrogen. This reaction goes very, very nicely. Only thing that's wrong with this is that pyridine kind of stinks, and so we don't really use it a lot in lab. In real lab you do, but not here, because everybody would smell badly for a week or so, even worse than usual. Any questions? All right, remember our alkyl lithiums. Remember we said this is a carbanion, isn't it? Carbanion can be a very good nucleophile, even if this is a really lousy electrophile. If you take 2 moles of alkyl lithium, the first mole, all it does is deprotonate this, make the anion, so you waste one. The second one, though, acts as a nucleophile, attacks, and you make the ketone. It's a nice simple way to make ketones from carboxylic acids. Go ahead and draw the product for this reaction. Our first ethyl group here does nothing more than remove this hydrogen. That makes it ethane, and it bubbles out. The second one, however, is now a nucleophile. It will attack the carbonyl carbon here and make the ketone. Here's the ethyl group that you attached to this carbonyl carbon. Any questions? All right. Back in chapter 17, we talked about making alcohols. We said we could make alcohols by reducing things with either lithyl or bore hydride. Turns out that one of the things you can reduce is a carboxylic acid. all in the world that happens here. All you have to remember is the carbonyl carbon becomes a CH2. Lithium aluminum hydride, carbonyl carbon becomes a CH2. Borohydride, same sort of thing. This is a derivative of a natural product called boreol. Go ahead and draw the product for this reduction. Now, why did I choose this particular compound? Because I want you to go through the agony of drawing the bicyclic ring. The agony and the ecstasy. Boreol is what's called a terpene, terpene derivative actually. And it's produced in plants and things like that. Polyterpenes, natural plant polymers containing double bonds. Isoprene is a classic example. Isoprene is actually emitted in ton quantities by the forests of the world. Not ton quantities. Did I say ton? I meant to say billions of tons a year. Now that's a whole lot, that's a simple hydrocarbon. That's a whole lot more than the gasoline that we spill on the ground. And yet it somehow goes and nobody cares. I don't know if any of you remember many, many years ago, somebody told this to Ronald Reagan, and that he did a news conference and he said that trees pollute more than we do. Actually, he was right, but they really made fun of him for it. But,
Is
all right.
Rubber, Dr. Young? Don't you make tires from trees? Like
Yeah.
rubber?
Yeah,
That's-
polyisoprene is natural rubber. Or a polyisoprene derivative is natural rubber. So, here we're going to reduce our carbonyl simply to a CH2. Either borohydride or lithium. Any questions? All right, the next reaction we're going to look at is actually a really neat reaction. It's important in organic chemistry and is actually very important in biochemistry as well. It's a decarboxylation reaction. In biochemistry, during normal metabolism, amino acids are decarboxylated. The mechanism is going to look something like this. What you need is a carbonyl that is beta to a carboxylic acid. Now remember when we do alpha beta, alpha is the first carbon, beta is the second. So a beta carbonyl acid. In this case, we have a beta diacid. It's called malonic acid. If you take malonic acid and acidify it a tiny bit, warm it up a tiny bit, you lose CO2, that's decarboxylation, and you wind up with a methyl group where our CH2 used to be. The mechanism of the reaction, it's a concerted magic step. What happens is, all at once, the electrons from the OH bond move in to form a carbonyl, that's going to be CO2. The electrons that were here in the carbon-carbon bond move in, these go up, pick up a proton. We actually make the enolate. The enolate then very rapidly converts to the carbonyl.
When an acid is present, you're saying?
Yeah, we need a touch of acid because it has to be the acidic form. Now, why does this happen? Think about hydrogen bonding. This hydrogen is living here right next to two oxygens, isn't it? So it's hydrogen bonded back through here. So it's a very stable arrangement. And hydrogen bonding gives it the kick that lets this happen. When we do alpha substitution in the next chapter, we'll talk about enolates like this and use those as nucleophiles. But right now, let's just do the magic. Again, this is malonic acid. It's a malonic ester, actually. In a malonic ester synthesis, what you're going to do is hydrolyze to give the acid. It's going to decarboxylate to form an enolate, which is going to be your nucleophile. Again, this is next chapter. The way this happens, in the presence of acid, we go to malonic acid. Again, these are esters. Remember we said with an ester, add acid and water, it goes back, doesn't it? To the acid. As soon as you get to the acid here, this is all set up for decarboxylation. This is the enol that we just formed. As this enol collapses, the electrons will come in and they'll be focused here. That will be our nucleophile in our next chapter. In this case, it's simply going to pick up a proton to give us the carboxylic acid. Malonic ester synthesis, again, that's something we'll do next chapter. Now, speaking of enolates, you can actually make the enolate anion of a carboxylic acid using a very, very strong base. So if we take a carboxylic acid like this, and we use lithium diisopropyl amide. Now, this is a nitrogen anion, isn't it? Think of OH, except maybe 10 times more basic. So it's really, really basic. This guy, 1 mole of it simply takes the hydrogen off. That's it. Get the amine, no problem. But the next mole is going to react to this carbon to give the enolate anion. This guy we will use as a nucleophile. Again, this is alpha substitution. We're doing that next chapter. But it would kind of look like this. If we took, see, here's our partial negative charge here. If we took an enolate like this, in the presence of LDA and bromine, we would make an anion. It would then attack the bromine, and you wound up with an alpha bromo acid. These are mentioned in this chapter, but again, we'll do this big time next chapter. Any questions? Well, just to make sure we got it, go ahead and predict the product here. LDA, we're going to make the enolate anion at this carbon. That's going to be your nucleophile, right? Here we have benzyl bromide instead of bromine. We know that this is very active towards SN2 reactions. So what's going to happen? Enolate anion is going to attack the CH2. Here's our enolate anion from this guy. The enolate anion is going to attack the CH2, bromine will leave, and our product will be our original acid with the benzyl group in the alpha position. Any questions? Enolate anion from LDA, simple nucleophile alpha substitution. Now the next two reactions really are things that you won't see very much, but they have history. The first one is called the Hell-Volhard-Zielinski reaction. And the reason that this makes all the textbooks is it just has a really neat name. And back in the old days, it was the excuse to use hell in class. What you're going to do is simply wind up with an alpha bromo acid. So just like we just did with LDA. In the Hell-Volhard-Zielinski reaction, you start off with a carboxylic acid and PBr3. Now, what did I tell you about PBr3? It converts the acid to the acyl bromide. So this all happens in one pot. One pot. Step one, we make the acid bromide. Once we get the acid bromide, this can spontaneously form an enolate, can't it? That means we have negative character right here. Our enolate then will attack, use the acid bromide enolate. This anion then will attack bromine that we throw in. Attacks here. We make the alpha bromo acid bromide. And the last thing you do is you take the whole mess and you add water. Just like an ester, if you add water and acid, it goes back to the acid. This works even better. Oof, you're at this point. Hell-Volhard-Zielinski. Again, you don't see it very often, but it's a really fun reaction to say, and it can actually be useful. It's just one ugly pot. Yeah.
On here you have CH3OH instead of H2O.
Mm-hmm.
Is that
That's
just a
why.
different?
Think about this. As our second step, instead of dumping in water, what if we dumped in alcohol? The alcohol will react with the acyl bromide to make an ester. So, using Hell-Volhard-Zielinski with water as a second step, you get the acid. If for a second step you dump in alcohol instead, you get the ester. So it's kind of a cute way to do it. The other reaction that you're not going to see very often is the Hunstecker reaction. Again, it's kind of a fun reaction. It's a decarboxylation. It's magic. You use heavy metal in the presence of bromine, warm it up, and what happens is you lose CO2 and put a bromine where your carboxylic acid used to be attached. You need a heavy metal. Mercury will work. Remember, all you're doing is splitting the CO2 off here, putting the bromine here. Lead-4 also works. Go ahead and draw the product for the decarboxylation. when you see Hunstecker conditions, you should just automatically say, we're going to lose CO2, replace the carboxylic acid with a bromine. Now, why would you want to do that? Well, we can do substitutions here now, can't we? Makes it nice and active. In this case, we're simply going to split off our CO2. Bromine is going to be attached here. And that's our product. Look at some sample reactions. If we take phenylethanoic acid in the presence of borohydride, we will reduce it. Chapter 17, right? Going to reduce 2 hydrogens here. We make the alcohol. Both of these are Hunstecker. This is actually the one from the previous slide, so we'll just do our product. Again, same bicyclic structure with the bromine there. You can also do this with lead 4. Again, add bromine, warm it up. Just split off CO2, bromine goes there, and you get isopropyl bromide. Now this next problem looks like a simple synthetic problem. It was actually it was actually a question verbatim from a final exam from 235. What you want to do is make these guys only source of carbon you have, only thing you have to work with is butanoic acid. Well, we look at our first reaction. What have we done? We have taken butanoic acid and we've taken the carbonyl and made it a CH2. We know how to do that. All we're doing is reducing it. We can reduce it either with lithium aluminum hydride or borohydride, butanoic acid, either lithyl or BH4 minus. These conditions actually we did not talk about in 234, but if you make a borane, BH3 and THF, then add acid, it converts it to the hydrochloride. We didn't talk about that though, so just change that to BH4 minus. Now, we need to start with butanoic acid and make 1, 2, 3, 4, 1 bromo butane. Now, how do we do that? Remember, it's a final exam, so you have to remember chapter 17 too, don't you? In chapter 17, we said we could take an alcohol and make an alkyl bromide with what? PBr3. So, step 1, reduce it. Step 2, alcohol plus PBr3 to make the alkyl bromide. And finally, we're going to go from butanoic acid to pentanoic acid. So we added another carbon here, didn't we? We know two ways to do this. If we were to take one bromobutane and react it with cyanide, we would make the nitrile, wouldn't we? Then, just like you're going to do on Wednesday, if we dump the nitrile in with strong acid, it will hydrolyze to the carboxylic acid. So, step one, add cyanide, make the cyanyl group, the nitrile. That adds our extra carbon. Step two, we hydrolyze to the acid. Now there's another way we know to do this, don't we? Carboxylation of a Grignard. Remember, you make the Grignard, then add little chips of dry ice. To do that, we want to take bromobutane, add magnesium, then react that with CO2.
For the second one, is there like a step missing, or how do we get from the starting one to the just the alcohol?
Well, the starting acid, step one, we have to reduce. Step two, we have to convert to the alkyl halide. Step three, we convert to the Grignard, then react that with CO2. Now, remember whenever you do a Grignard, the last step is always to dump the whole mix into aqueous acid. And that's where you get the proton from this. But that's called a workup step. That's automatic. All right, reactions of nitriles. Not going to have a whole lot to do here. We already know some of these. Step one, or reaction one. If we take a nitrile, strong acid, we get the carboxylic acid. We've done that. These two are new. We'll talk about these in a second. If we take a nitrile with lithyl, we convert this carbon into a CH2. So we make the amine. This is diisobutyl aluminum hydride. It's like lithyl, except it is a really rotten reducing agent. This will take the nitrile and stop at the aldehyde. We'll see how that happens. And finally, if we take a nitrile with a Grignard, we'll see we can convert this into a carbonyl carbon and add our Grignard to it. So just a couple new reactions here. We talked about this one. Again, we're doing this on Wednesday. Grignard. We know our Grignard reagent is a stabilized carbanion, right? As such, it can attack the nitrile carbon. Think of this as kind of like a carbonyl twice over. When the Grignard attacks, you get this intermediate. Now, I've shown this as an anion because that's exactly what it is. We add the anion, we get an anion. But because this is anionic, and this is one heck of a strong base, this has absolutely no interest in adding another electrophile. It just sits there now. It sits there until we take it and we do our magic workup step where we dump everything into aqueous acid, right? This is an imine then. We will protonate this to the ammonium ion. Now, this was totally unreactive. This is very, very reactive. Imines, we know, react with water to give carbonyls. Bottom line, take our R group, convert the nitrile carbon to a carbonyl, and here's our R that we've added. Nice, simple way to make ketones. Any questions? Let's do a two-step synthesis here. We're going to start with styrene, and we're going to make a methyl ketone. If you do the body count, we've added 2 carbons to our chain, haven't we? 2 carbons. Well, we peek at our starting material, we look at this, and say, what in the world have we done here? We have to add 2 carbons. This is a chapter on carboxylic acids and nitriles. So we know that we can add one of the carbons as cyanide, our nitrile. So if we had a nitrile, we could make a methyl ketone using the reaction we just saw. That is reaction with the Grignard. So our plan here for our step going up this way, we want our carbon skeleton, except this is going to be a nitrile carbon. Go ahead and draw the structure of the nitrile and the Grignard that you would need to do this reaction. And our intermediate. This is a nitrile carbon. Methyl group we added from methyl magnesium bromide. This is our nitrile, our Grignard reagent, simply methyl magnesium bromide. All right, so we need to make a nitrile now, don't we? Think way back to chapter 6 or 3 or 2 or whatever. We make these by SN2 reactions, right? So we need a leaving group of some sort here. We could do that with a halogen. Going to simply react it with cyanide. We're going to do this as an SN2 reaction. So what we want is a halogen here. Cn minus is our nucleophile. And that ought to do it. Finally, we are converting an alkene into an alkyl bromide. What kind of alkyl bromide is this? Remember that from chapter 6-ish. Is the bromine attached to the carbon that would give the most stable carbocation? No, that would be the benzyl carbon, right? So this is an anti-Markovnikov alkyl halide. How do we make that? Radical reaction. The conditions, simply HBr in the presence of peroxides. So going forward, take styrene, HBr peroxide, make the bromo alkane. React that with cyanide to make the nitrile. Add our second carbon as a Grignard and make our carbonyl. Isn't that fun? Let's do one more. Remember we said that you could use lithiol or diisobutyl aluminum hydride to convert a nitrile and make it into an amine. With lithiol, this becomes a CH2. So we get a primary amine. Diisobutyl aluminum hydride looks like this. Here's our aluminum. We have these big, ugly isobutyls on it. That's what slows it down and makes it a very cumbersome reducing agent. What happens here is that only one hydrogen is transferred. If we only transfer one hydrogen, we would make the aldehyde equivalent of a nitrile anion. This again is going to be an imine anion. Dump it into water and we make the aldehyde. So a very cumbersome reducing agent. We stop at the aldehyde, powerful reducing agent, all the way to the amine. So let's use this in a synthesis. Starting off with this guy, and we're making this one. We have added a carbon and a nitrogen, and we have converted our carbonyl oxygen to a CH2. We've done 2 bits of magic here. As always, we want to start with our last reaction. This is the addition of a carbon and a nitrogen. That should scream at you, nitrile, right? So if we had a nitrile, we could reduce it to make the primary amine. Go ahead and draw the structure of the nitrile that you would need. All in the world you have to do is convert our CH2 to the nitrile carbon. This is the nitrile nitrogen, and it should look like that. Lithiol is the reducing agent we want. Remember, lithiol was more selective than boryl hydride and won't really touch the double bond. Now is where you get to use a little bit of real synthetic logic. We have to do 2 things to our starting material to get here, don't we? 2 things. We have to add the nitrile. We can do that with SN2, we know that. We also have to convert the carbonyl oxygen to a CH2. Now, remember chapter 18 or 19. How do we do that? The Wittig reaction. Right? The Wittig reaction. So we have to do two things. This carbonyl has to become a CH2. We could do that with a Wittig reagent. We have to somehow get Cn minus ion. Now in the last one we did that with a simple SN2 with cyanide. Remember back in chapter 19, there's another way we could add cyanide, and that was conjugate addition. We have an alpha-beta unsaturated ketone here. We can add cyanide to this carbon. But we have to do this while this is still a carbonyl. Therefore, the Wittig must happen here. Cyanide addition must happen here. Appreciate the logic here. You need the alpha-beta unsaturated carbonyl to add cyanide. Then you can get rid of it with the Wittig. All right, so our Wittig reagent is simply going to be a CH2, isn't it? Attached to a triphenylphosphine. And it's going to look like this. Here's our compound. Again, we have simply changed the carbonyl into a CH2. Our Wittig reagent is our CH2 that we add, triphenylphosphonium yellow. And finally, in order to add this stuff, we need to add this to our beta carbon. That's chapter 19. And we can do that with either HCN, that's a little clumsy. We said that diethyl aluminum nitrile is a better reagent. So we'll use that. Again, the Cn minus adds to the beta carbon to give our product. So our full synthesis, we do a beta addition of our chapter on ketones and aldehydes. We do a Wittig reaction, same chapter. Once we get the nitrile, simply reduce it off with lithal, and that's this chapter. Any questions? All right, just a handful of new chemistry in this one. Again, none of the reactions should have been real surprising. We will talk a lot more about acyl transfer in the next few chapters, where we do tetrahedral intermediates that collapse to form products. Remember, on Wednesday, we will do the lab on page 346. And that is hydrolysis of benzonitrile to benzoic acid. It's not difficult. What you do is simply take benzonitrile. Now we will double our quantities. So again, we have good stuff to work with. Going to add phosphoric acid and reflux for about 45 minutes. So remember how to set the reflux apparatus up. It's nice and vertical. After it is cooked, you simply take your